we've seen then that the condition that the acceleration of the planet be back toward the sun and have this magnitude results in this equation, and we observe that we have that this side is a multiple of UR. This side has a multiple of U theta. Now U theta is perpendicular to UR, our unit vector in the R direction, our unit vector in the theta direction, have been defined to be perpendicular. So this side has no component in the direction of U theta. If these sides are equal, that means this side has zero component in the direction of U theta, so that the coefficient of U theta has to be zero, giving us this equation. Now we've also got this equation. Turns out we're not going to be able to do too much with this equation. It really requires a deeper knowledge of differential equations than we can assume in this course. But we can deal with this one. And we just blurred the screen out. So let's see if we can recapture focus. Come on. There we go. This equation tells us that, well, this equation involves d theta dt and the second derivative of theta with respect to t. This is the derivative of this. So if we let w equal d theta dt, then second derivative of theta with respect to t is dw dt, and we can rewrite our equation as 2r prime times w plus r times dw dt equals 0. And should have written it this way in the first place, but r prime is just dr dt, so we have 2 dr dt w plus r dw dt equals 0. We can rewrite this. Let's just take our dw dt and subtract it from both sides, so it'll be on this side, and leave our dr dt term on this side. We get 2w dr dt equals negative r dw dt. And then let's simply divide both sides by the w and by the r, and we get 2 over r times dr dt equals negative 1 over w times dw dt. Now, we're going to pull a trick that you might or might not have seen. We're just going to integrate both sides of this equation, and I'm going to wave our hands a little bit and say, well, you've got a dw here on both sides, so the dw is going to go away, or the, not a dt on both sides, so the dt is going to go away, and we end up with 2 over r dr equals negative 1 over w dw. We put an integral sign in front of these terms. Probably should get some parentheses in here. And we just do the integration. We get 2 times the natural log of the absolute value of r equals negative natural log of the absolute value of w. Now, if we assume r and w are both positive, which we can't really necessarily do because w is d theta dt, and our r function might have a theta function that's moving in the negative direction, but let's again wave our hands just a little bit. So the natural log of the absolute value of r is equal to just natural log of r, and the absolute value sign can go away over here also. So if r is greater than 0 and w is greater than 0, we get the natural log of r on this side and a natural log of w on this side. Now we know that 2 times the natural log of something is a natural log of the square of that thing, and negative natural log of a quantity is the natural log of the reciprocal of the quantity. And if you're not sure about those laws of logarithms and how they're related to the laws of exponents, you should consider reviewing this. But this follows from the laws of exponents through by way of the laws of logarithms. So that r squared equals one over w, and I've gone and forgotten my integration constant, which we're going to need. So I'm going to say plus c. Put a little dividing line here. Okay, where c is an integration constant that absorbs the integration constants from both sides. And when we exponentiate both sides, okay, which is what we do to get from this step to this step, we're going to have to exponentiate natural log of 1 over w plus c. Let's write that down here. E to the natural log of r squared equals r squared. E to the natural log of 1 over w plus c by the laws of exponents is e to the c times e to the natural log of 1 over w. E to the c for any value of c, and c is an arbitrary constant, is a positive number, and we're going to replace e to the c by a. E to the natural log of 1 over w is 1 over w, and a is going to be understood to be greater than 0. So that we're going to get r squared not equal to 1 over w, but a times 1 over w, and I'm going to change that to a over w with the proviso that a is greater than 0. So our condition on the equation that the force be radial toward the origin results in this being the coefficient of the u theta vector being 0. This leads us to this equation. It's rather easily solved. I've complicated it a little bit by forgetting the integration constant, but this is our solution. So r squared is a over w. Now we're going to pull that back into the situation and see what that tells us about the motion of the planet.